All right. Welcome back. Hello. Uh, what we're going to do, this, you might be thinking or wondering if this video is out of order. The one you should have watched right before this is 8.5. Um, I have my reasons, but I'm going to go ahead and jump to section 8.8, which is what we're going to do for the next couple of videos. Just because I think it progresses nicely into 8.6 and 8.7, which will finish out chapter 8 for us. So in 8.5, we talked about factoring and factoring trinomials, and we did this whole thing where it's like what multiplies to C and adds to B. 8.8 is it's still factoring. It's just a new method of factoring. And so it's called factoring by grouping. And it'll take a little bit of practice to get used to, but then we'll kind of see that it works out nicely once we get the hang of it. So our EQ is how can I factor higher degree polynomials using grouping? And remember, degree just means power, essentially. So everything we did has been power 2, like x squared. And then here today, we're going to go a little bit higher with that. So to get started, this has nothing to do with factoring. This is just reminding ourselves from earlier in the chapter what it means to add polynomials together. And adding polynomials basically just means we're combining like terms. So here I have 2x to the third, and I'm going to add another 9x to the third, which would be 11. 9 plus 2 is 11. But when I'm adding, I don't change the exponents. I keep that the same. My next highest term or highest power that I see is negative 15x squared. There's no x squareds in the rest of the problem, so that's going to stay by itself. Then we move over to plus 11x, which again is a loner. There's no other term that can combine with it. And finally, I have 16 minus 18, which is negative 2. So this is our answer or our expression after we add those two together. What we did is, if it was subtraction, if you recall, we're going to change that minus sign because this minus sign essentially has to distribute to everything in the second set of parentheses. So instead of doing that, what I like to do is change the minus to a plus. And then we're just going to go ahead and switch the sign of everything in the second parentheses. So negatives become positives, and positives switch to negatives. Now the first polynomial, the first set of parentheses, does not change. So we'll keep that the same. And now we're going to do the same thing we just did. We're going to combine like terms. I have positive 4x to the fourth and negative 7x to the fourth. So it's going to be negative 3x4. And if you recall, it's called standard form, where we go highest power to lowest power. And that's what I'm doing. So I started with power 4, and now I'm going to combine these two terms in orange. Negative 10 plus 12 is positive 2. X to the third. Then I have 12x and 3x, which is 15x. And finally, we have this minus 10 that's all by itself. So this is our final expression that we're looking for. Okay. So that's adding and subtracting. Let's get into the new stuff. Okay. This technique of factoring by grouping is very specifically for when there are 4 terms in the expression. Okay. This method only works if there are 4 terms. And basically what we're going to do is we're going to split the problem in half and look at the first 2 terms, and then we'll move to the last 2 terms. Okay. So what I'm going to do is I'm going to put a little dividing line right after the second term, which is minus 6n. Now notice I don't want the line here because I want to make sure that it's clear that positive or that plus sign belongs with the 1n. Okay. And you might be saying to yourself, well, we can combine those together, but just bear with me for a minute and we'll see kind of how we can do this factoring by grouping thing. Now what I'm going to do is I'm going to just look at the first 2 terms. Okay. So I'm only concerned with these 2 terms right now. I'm going to pretend like the other 2 terms don't even exist. And so I'll do that here. Okay. What I'm going to do is I'm going to check, is there a greatest common factor? Is there a GCF for just those 2 terms? What do they have in common? Well, the number or the coefficient, I can divide those both by 2. So I know 2 is part of my GCF. but they also have the variable n. The first term has n squared. The second term has just a single n. So that means all I can take out is n to the first power as part of my greatest common factor. Then I'm going to put what's left. 2 divided by 2 is 1, which isn't necessary. I had n squared, but I took one of the n's away. And then here, instead of minus 6, I have minus 3. Okay, that's all we're going to do for the first half. So we factor the first half. That's done. We're now going to transition to the second half of the problem. And we're going to do the exact same thing. We're going to say, what do these two terms have in common? And the first term and the second term have nothing in common here. Because of the coefficient of 1, there's nothing I can divide. So I'm going to go ahead and just put a positive 1, which might seem kind of silly to take out a 1, because what happens if I divide by 1? Everything stays the same. But there will be a reason for it in just a second. Okay. So we did the GCF of the left half, and we did the GCF of the right half. I'm just going to highlight this to show that they're separate. Okay. Now, this idea of factoring by grouping is awesome, because if we've done it correctly, and if factoring by grouping will work, then what's in the parentheses of the two halves of our problem should match. Okay, and here we see, hey, look at that. It's 1n minus 3 on both sides. Okay, and since we are factoring, my answer is still going to look like two sets of parentheses, like two binomials. And what's going to happen here, and this is the part that might be a little confusing right away, is that 1n minus 3 that's written on both sides of the problem is one of my factors. Okay, I don't write it twice, even though I see it twice, right there and there. I'm only going to write it one time. The other binomial, I'm going to take the GCF from each half of the problem, and together that will make my other binomial. Okay, so the factored version of this is what's in parentheses right there, 1n minus 3 times 2n plus 1. Now, you could go ahead and distribute to check your work, but that right there, this thing right here is what we're looking for. It is two sets of parentheses that, if multiplied together, will give us back the original problem that we were started with. Okay, so let's see that again. Let's look at another example. Again, 4 terms here. If you see 4 terms, you should think right away, I'm going to factor by grouping. So again, I'm going to split the problem in half into 2 sets of 2. Then I'm just going to focus on the first 2 terms. And what did these 2 terms have in common? Well, the coefficient, I can divide both of those by 3. And both terms have n. How many n's can I take from both of those terms? Well, there's 3 n's here and 2 n's here. So I can take n squared, or 2 n's, from each term, which will leave me with 3 divided by 3 is 1, 12 divided by 3 is 4, and there's no n's remaining here because it was n squared. Okay, so that's the first half of the problem. Now we do the same thing with the second half. What does 2n minus 8 have in common? Well, I can divide both the numbers by 2. I can't put n there because 8 is without the variable. So then in here it would be 1n minus 4. And again, if you want to just put n minus 4, you can. It's totally fine. We check to see, hey, look at that. Convenient. The 1n minus 4 and the 1n minus 4 match, which is awesome. That's what we want to see. So that's one of my factors of my final answer. And then my GCFs are going to come together to form the other binomial. So 3n squared, and that's a positive 2. Okay, so that's the idea with factoring by grouping. Split it in half and then just treat it as 2 miniature problems. And as long as the parentheses that are highlighted, right, this right here, as long as those are the same, then you know you've done it correctly and that it can be factored using this technique. Okay, so go ahead, pause real quick and see if you can try this problem. All right, so if I split this in half, and again, I'm not going to zoom all the way in. If I just focus on the first half of the problem, 2t to the third and 8t to the second, my greatest common factor is going to be 2, and then I can take t squared from each, which would leave me with 1t plus 4. Again, now I should be expecting to see 1t plus 4 in the second half of this problem. Okay, 3t and 12 both have a 3 in common, and if I take out or divide by 3, sure enough, I get 1t plus 4, which is fantastic, because then the factored version is going to be 1t plus 4 times 2t squared plus 3. And that's our factored version, or factored expression. Okay. Now, just real quick, we want to take a look at what happens with negatives. And we've had negatives in these examples. If you go back, right, we had some minus signs in here. But both halves of the problem started with a positive number. And what we're going to see is what happens if, when I split it up, one of the halves of the problem is starting with a negative. Okay, so if I split this down the middle, okay, I see that these two terms, I can divide them both by 4. One has t to the third, one has t to the second, so I can take out t squared, and that would leave me with 1t minus 3. Now here, in the second half, is where it gets a little interesting. First of all, if there's no number in front of a variable, remember, we can always put a 1. But now, what's the greatest common factor of those two terms, of negative 1t and positive 3? There's nothing in common. So just like we did earlier, I'm going to take 1 out and basically just rewrite the problem. But because I am starting with a negative number, I'm going to take out the negative as part of my GCF. So I'm going to divide by negative 1. Okay. And what that's going to do is, by dividing by negative 1, my parentheses will now match from the first half. Okay, so if I divide by negative 1, that'll give me 1t. And then positive 3 divided by negative 1 will switch to minus 3, which is perfect because now my parentheses match. If I wouldn't have taken out the negative, and if I had just written positive 1 right here, the parentheses wouldn't have matched, and then bad things happen. Okay, so my factored version will be 1t minus 3 times 4t squared minus 1. And this is what we're looking for. Okay. So if half the problem starts with a negative, just make sure to include the negative with the GCF. So go ahead and give this expression a try, and then we'll be done. All right. So there's my split. Again, I could combine these like terms, but just play along because there will be a reason that we're doing this down the road. So if I look at the first half, 2 and 3 don't have any number in common. So it's the number portion of the GCF will be 1. I'm going to take out a single t, which will leave me with 2t plus 3. Okay, so there's the first half. And for the second half of the problem, negative 10 and negative 15, because I'm starting with the negative 10, I'm going to take out the negative as well as the 5, which is the number that can divide both 10 and 15. So if I do this, check, hopefully I get 2t plus 3, and sure enough, if I divide both those numbers by negative 5, I'll get 2t plus 3, which means 2t plus 3 times 1t minus 5 is my factored version. Okay. Again, you can always check your work by just going through and doing distribution on your answer to see if you get back the original. Okay. So to summarize, how can I factor higher degree polynomials using grouping? Grouping only works with 4 terms. We're going to split into 2 sets of 2 terms, and then we're going to find the GCF. Find GCF of each half. We'll expand on this a little bit more in the next video, but for now, we're good.